Okay. So we had seen in the last class about a simple continuous wave radar and a Doppler, pulse Doppler radar, whose equations, pulse radar that uses Doppler frequency shift. That also we had seen. And for continuous wave radar, even though the block diagram is very simple, working is also simple, there are certain limitations. It's a most basic one. We have certain limitations, and these are the main limitations of a continuous wave radar. What are they? See, there is no isolation between transmitter and receiver. Lack of isolation between transmitter and receiver, which causes the receiver to burn out in a case of large transmitter powers. When you use a continuous wave radar for long range applications, for the defense, space surveillance, or ballistic missile detection purposes, it has got several limitations. First limitation is that there is no isolation between transmitter and receiver, which causes receiver burnout. Then second is introduction of noise known as flicker noise for the type of receivers known as homodyne type of receivers. You know, you have heterodyne and homodyne type of receiver. We'll be coming to that later. So here there is the introduction of flicker noise effect, which is also a disadvantage. Then there is no matched filter in the receiver, so it is less accurate. So accuracy is affected here. No matched filter in the receiver. Then lack of knowledge as to whether the target is approaching or receding. You only get an idea about FT, no sign, because we cannot indicate whether the target is coming towards us or going away from the radar. Okay. So lack of knowledge. Then increased clutter compared to pulse radar. That is, clutter means the echo signal that is received from unwanted surroundings and around the target, unwanted sources. So that is clutter noise. So increased clutter, such clutter effects are not suppressed in a proper way when compared to a pulse radar. Pulse radar does that in a better way. Then no measurement of range to target. You cannot measure the range. So these are the limitations of a continuous wave radar. You will be asked to describe the limitations of a continuous wave radar. And this isolation can be obtained or improved by using separate antennas, which becomes costlier or expensive. Usually we use the same antenna, but to provide good isolation, we can have separate antennas for transmitter and receiver. And it can also be achieved by using FM for continuous wave carrier modulation. FM is used for continuous wave carrier modulation, resulting in an FM CW radar. And FM CW radar also makes measurement of range possible. Then flicker effect can be avoided by replacing the homodyne receiver with a super heterodyne receiver. This flicker effect, second disadvantage. You can use a super heterodyne receiver, which is done in the continuous wave radar with non-zero IF. That is, you modify the simple continuous wave radar by making certain improvements to overcome these limitations to an extent. This isolation, lack of isolation can be overcome by using separate antenna. Then flicker noise effect can also be avoided by using heterodyne, super heterodyne type of receiver, because this type of noise is usually present in homodyne type of receiver. You replace it with a heterodyne type of receiver that can avoid flicker noise effect. Then we can measure range by using FMCW radar. So if FMCW radar working, if you are asked to describe a radar which makes use of the or which measures the range, then you have to explain about FMCW radar. So measurement of range is possible in the type of radar known as FMCW radar. Okay. And okay, that's all for the limitations. Now moving on to the next type of radar, that is continuous wave radar with non-zero IF. This is the one which avoids the flicker noise effect, where you have a super heterodyne receiver and it has a non-zero IF. IF stands for intermediate frequency. That is, you mix with a local oscillator signal and convert to an intermediate frequency. That's the working. So continuous wave radar with non-zero IF. So you have the block diagram here. This is the continuous wave radar block diagram with non-zero IF. Okay. With CW radar with non-zero IF. So look at the block diagram. You have two separate antennas so that good isolation is obtained between transmitter and receiver. They have their own local oscillator sources. See, continuous wave transmitter, which transmits at a frequency of FT, the transmitter frequency. Then the transmitter mixer is there, which is mixed with the local oscillator signal, and it is the intermediate frequency. It is given that Ft plus Fi is given as a reference to the receiver antenna, where you receive the input signal shifted in frequency by an amount Fd, Doppler frequency, because it is a moving target. The frequency gets shifted by an amount plus or minus Fd. So transmitted frequency is at Ft, it is received back at Ft plus or minus Fd. Then this local oscillator gives us the intermediate frequency from which Ft plus Fi is given as receiver to the given as reference to the receiver mixer. Then it is mixed with the incoming signal, and that Fi plus or Fd plus or minus Fd is taken. It is the intermediate frequency shifted by Fd, amplified, then demodulated to remove the carrier, and Fd alone is extracted by means of the Doppler filter. Then again unwanted noise is removed here by means of the Doppler filter, and it is given to the display. This is how the block diagram looks like. Continuous wave radar with non-zero IF. That means an IF is present. So the receiver operates with a non-zero IF. Separate antennas are used for transmission and reception. The use of intermediate frequency in the receiver minimizes the noise effects. Flicker noise effects are minimized in this super heterodyne type of receiver. And a small portion of the transmitter output is mixed with a local oscillator signal, that is Ft plus Fi, and the sum is fed to the receiver mixer. The receiver also receives the Doppler shifted echo signal, that is Ft plus or minus Fd. This is amplified, demodulated, then Doppler frequency is extracted by the Doppler filter, and the output waveform is displayed on the radar display. But what here also we have the disadvantage that the sign of the Fd is lost. Okay. So this is the explanation for continuous wave radar. Usually ask for your exam, you'll draw the block diagram of a continuous wave radar with a non-zero IF and explain its working. Okay, this is the that type of radar. Now moving on to the next type, let's see, which is a moving target indicator radar. It is usually a pulse radar, special type of radar known as moving target indicator radar, or MTI radar. MTI, moving target indicator radar. So block diagram, I could have drawn it earlier, but didn't get time. You have a pulse modulator first, then from the antenna, common antenna, same antenna is used. You use a duplexer, then you have a power amplifier, from duplexer it goes to the mixer, then this is Stalo, STALO, it goes to the mixer again, FL, this is the frequency here, FL plus FC, this FL plus FC plus FV. Then from mixer, the output IF amplifier. This is FC plus or minus FD. Then it goes to a phase detector. Output is FD. And here also you have a reference signal which goes to another oscillator known as Coho. JLO and Coho are the two important parts of this radar. This is the reference signal. Yes. So this is FC. So this is the block diagram. This goes to BLC. BLC is delay line canceller. We'll come to that later. Delay line canceller is an important part of a radar used for separating Doppler frequency. Delay line canceller. So this is the block diagram for a moving target indicator radar, MTI radar, which consists of two separate oscillators named as Stalo and Coho. Stalo and Coho. Stalo stands for stable local oscillator. Coho stands for coherent local oscillator. These are the two names of the local oscillators used in the MTI radar. Okay. So there will be such questions are asked for Viva. Stalo and Coho are important in the construction of which type of radar. It's a moving target indicator radar. So the local oscillator, here they are very much stable, accurate and precise. You need a very stable oscillator for this case, and it also needs to be coherent, highly coherent source of oscillation is needed here. So the local oscillator used in MTI radar, it needs to be more stable than the oscillator used in a radar which does not employ radar. If the phase of the local oscillator were to change, if phase changes, it is in case the local oscillator which we are using, it is having a non-coherent phase, then between pulses, then what happens? Like say phase changes, the clutter residue will result. That is, clutter will not get cancelled out properly. So phase should be very stable. In case of a non-coherent phase local oscillator, clutter will be present. So in order to avoid clutter residue, you need a highly coherent local oscillator. And clutter output can result at the output of the delay line canceller, which can be mistaken for the moving target, even though only clutter is present. So always you need to remove noise from stationary targets known as clutter. Otherwise, it can be mistaken for a moving target. If the phase changes, it can cause erroneous reading. So phase needs to be very much coherent. Hence, we need a very stable local oscillator known as stay low, which is used here. That is stay low at a frequency FL. And the intermediate frequency state is designed as a masked filter instead of amplitude detector. IF amplifier is usually a masked filter instead of a common amplitude detector. And there is a phase detector following the IF amplifier. Separate phase detector is there. This is a mixer-like device which combines the received signal at IF and the reference signal from the coho. Coho is the coherent oscillator. It combines the output from the IF amplifier and output of the, that is phase detector combines the output from the IF amplifier and this reference signal from the coho. The output of the phase detector is the difference between these two and is equal to the Doppler frequency. Doppler frequency is extracted out here. It's equal to FD here. And in this sense, it is the reference signal that has the phase of the transmitted signal here. And the sum of coho and stay low signal here, FL plus FC, sum of this added, they are added and it is given as input to the power amplifier. The transmitted frequency is FL plus FC. The combination of stay low and coho is sometimes called the receiver excitation portion of the entire radar. And using the receiver, stay low and coho to generate the transmitter signal, it ensures better stability than if the functions were performed with two different sets of oscillators. You combine them together, so one is very stable and another at very coherent phase. So it is ensured that both stability and coherence is obtained. So that mixed signal is applied to the power amplifier, which usually we call it as a receiver excitation portion. So it ensures better stability than if the functions were performed with two different sets of oscillators. The output of the phase detector is input to the delay line canceller, and this delay line canceller, it acts as a high pass filter to remove or separate the Doppler shifted echo signal from unwanted echoes of stationary clutter. Only those which remain stationary, they will be removed. So delay line canceller is working like a high pass filter. In the MTI radar, the pulse repetition frequency is chosen so that there are no range ambiguities, no doubts about the range or errors in the range measurement. We have seen earlier what is meant by ambiguity in the measurement, about unambiguous range, maximum unambiguous range, etc. What causes that? Because if we choose the pulse repetition frequency to be too low, then because that echoes might occur as multiple time around occurs or second time around echoes. They might, that is after the transmission of the first pulse, after the transmission of the second pulse, you might get an echo from the, which is actually due to the transmission of the first pulse, which can be mistaken. Such echoes we call as second time around echoes. So if you choose, only if you choose the pulse repetition frequency correctly, you can avoid such ambiguities. So here in the MTI radar, always choose the PRF so that there are no range ambiguities. But what causes a disadvantage that is caused in the MTI radar is what is known as a blind speed. If the blind speeds we can tolerate, then MTI radar is an excellent method of moving targets in the presence of clutter. What is blind speed? We will see that. Here, the disadvantage which occurs is blind speed. That is, certain targets moving at certain speeds, they might not be detected. Blind speed occurs even in the case of automobiles, that is, or blind range. Some when you look in the mirror, at some rear view mirror, when you are driving a vehicle, there are some positions where you cannot see the vehicle that is coming from behind, isn't it? Such ranges we call as blind range. Even though the mirror is expected to cover the whole of the back, you might miss certain at certain positions, you miss the vehicle that is coming from or overtaking you. That can cause accidents. Same thing happens here also. Certain targets which are moving at blind speed, that is certain multiples of the frequency that is used, they can be uh, missed. You will miss detecting them. So such blind speeds is a problem in the case of MTA radar. If such blind speed problems can be avoided, then always the MTA radar is an excellent choice for detection of moving targets in the presence of clutter. Okay, that is it. Now, what is blind speed and what is a delay line canceller? We will see. And this is MTA radar, which is having a coherent local oscillator source. Now, one more type of MTA radar is there. We will see that also. This is known as non-coherent. So this one was, the one which we saw just now was coherent MTA radar or simply MTA radar. Now, non-coherent MTI radar. Very simple block diagram for that. Duplexer, power amplifier, power amplifier, modulator, then mixer, local oscillator, IF amplifier, amplitude detector, and delay line canceller. This is the simple block diagram for a non-coherent MTA radar. Here there is no condition about maintaining the coherent. The local oscillator need not be very coherent. So the coherent MTA radar, which uses the reference signal from an oscillator whose phase is same as that of the transmitter signal. That is how it was ensured. Coherence was ensured in the case of coherent MTA radar. You have the transmitter phase and the reference signal matched in phase. Here, in that case, the echo signal from clutter also has the characteristics of the transmitted signal and can be used as a reference to extract the Doppler frequency shift of the target echo signal. Since the clutter echo and the moving target echo appear together at the input of the receiver, and an internal reference signal is not needed. Okay. The radar that uses the clutter echo as the reference signal to extract the Doppler shifted target echo is known as a non-coherent MTI radar. Here, a reference signal itself is a portion of the signal, Doppler shifted target echo. A portion of that is taken and it is used to extract the actual signal. So a radar which uses the clutter echo as the reference signal to extract the Doppler shifted target echo is known as a non-coherent MTI radar. It is also called externally coherent MTI radar because you are using an external signal, also known as externally coherent MTI radar. So the other one was internally coherent. Okay. The block diagram is very much similar to a conventional pulse radar, except for the MTI filter which is usually replaced by a DLC. And you have a delay line canceller here, which we did not use in the case of pulse radar. The detector following the IF amplifier is a conventional amplifier, amplitude detector, rather than a pulse detector, which requires Coho as a reference. The detector is a non-linear device which multiplies the clutter signal and Doppler shifted moving target signal to produce the Doppler frequency, which is then extracted by the MTI filter. Okay. And the working is almost similar to that of a pulse radar. That is a signal that is mixed with the clutter is given as reference here, that is this local oscillator signal. It is an external signal mixed in the receiver mixer, then IF amplified, then it is extracted out conventional amplitude detector, then given to a delay line canceller, which will remove the clutter echoes. This is also known as an externally coherent MTI radar. So for more explanation, you can refer to the textbook by Skolnick. Okay, I have taken this from there only. So today we have seen about disadvantages of continuous wave radar, limitations. Then we have seen about continuous, how we can overcome them. Many of them, some disadvantages can be overcome by using a continuous wave radar with non-zero IF, or which uses a super heterodyne receiver instead of a homodyne receiver. It's working, we have seen. Then a moving target indicator radar, which is used to detect the presence of a moving target. But all these radars cannot calculate range. If you want to calculate range, then you have to use the FMCW radar. Then in the case of moving target indicator radar, you have stable oscillators, coherent local oscillators, which we use a very stable signal, internally generated signal as the reference, and to indicate the Doppler shifted frequency FD. And if we are using another a copy of the external signal, that is clutter echo, properly extracted clutter echo is given as a reference, and using that you separate out the Doppler shifted frequency, then you have a type of radar known as non-coherent MTI radar or externally coherent MTI radar. Okay. So that is all for today. We'll stop here.